Welcome everyone to the statistics seminar. Today is my greatest pleasure to introduce our speaker, Sivaraman Balakrishnan. Sorry, I'm pronouncing it from CMU. And Siva is currently an associate professor of Department of Statistics and Data Science, and jointly with Machine Learning Department. And Siva received his PhD from CMU in Computer Science, and then he did his postdoc with Bing Yu and Martin Wainwright at Berkeley. And then after that, he joined back to CMU, and then he worked on all kinds of exciting topics in statistical machine learning and algorithmic optimization problems. And today he's going to talk about assumption-light inference. And let's welcome Siva.
Thank you, Yanchi. Okay, so thank you for the invitation. Thank you for the introduction. Okay, so as Yanchi said, today I'll be talking about assumption-light inference. During the talk, just feel free at any point to unmute yourself and ask your questions. I won't really be monitoring chat, and I love interactive talks, so please feel free to interrupt. Okay, so let me first begin by acknowledging co-authors. I will talk about two pieces of work today. One is called the Hulk, and the other is called Universal Inference. So one of them is joined with Adi and Larry, and the other is joined with Arun and Larry, all of whom are colleagues at CMU. Okay, so let me start off with an outline for what I'm going to talk about. So I will first motivate the so-called assumption-light inference philosophy. I'll tell you what I mean by that phrase. And then I will motivate some of the methods that I will discuss by presenting some challenging general purpose inferential questions. So some things that will be sort of hard inference problems, and I will use them to motivate the methods that I will discuss. And the two methods that I will discuss, one of them is called universal inference. You should think of it roughly as a new way of doing likelihood ratio based inference. And the other will be this Hulk thing. And you should think of it as some sort of slightly different take on resampling methods, which is things like subsampling and bootstrap. Okay, so let's get started. So first, let me tell you a little bit about what this assumption-light philosophy is. So what is it that we actually want when we're talking about assumption-light inference methods? So what I want is methods to either construct confidence sets or to perform hypothesis tests. And I want them to satisfy some set of desiderata. I would like them to be transparently valid. That is, it should be easy to confirm that they are in fact valid. Ideally, they should be finite sample valid under very weak or essentially no assumptions. This is my first thing that I would like. The second is that I would like the methods to be somehow general purpose. That is, I would like them to apply to some big class of problems so that it's not just that I found one single hard inference problem and I solved it with this method, but I would like them ideally to be things that one could apply to many different types of problems. And finally, okay, they should be somehow easy to use. This is related to the first point in some way. But what I mean more precisely here is that I don't want to have to sit down and do some complicated variance calculation or something like that. I would like the method to be somehow easy to use. And okay, what am I willing to give up to get all of this? And this will be part of this philosophy that what I want is assumption-light validity. So the method should be valid. It should control the type 1 error correctly, or if it's a confidence set, it should have its advertised coverage. And what I'm willing to give up in some cases is statistical efficiency. It doesn't have to be optimal for every single problem, but ideally, hopefully, I'm not going to pay too large a price, but I'm willing to give up on some notion of optimality in the type 2 error or some notion of optimality in the size of the set. And this point, the fact that I'm willing to give up something will allow me in some way to use sample splitting in both cases, in both the methods that I discuss, but I'll do so somehow carefully. And part of the talk will be to try to convince you that there will be many examples where the statistical price that you pay in order to get all of the first few things, all of this assumption-light validity, the statistical price will be in some sense small. Okay, so that'll be part of the talk. I'll try to convince you that it'll be not as large as you would think a priori. All right, hopefully I've convinced you that, okay, if nothing else, there's some interesting trade-off here. That is, I will get something and maybe give up something, and hopefully it's up to you to decide whether it's useful or not, but maybe it is. All right, so in order to motivate more precisely what I'm going to talk about, I'm going to tell you a little bit about some hard examples. I will try to explain to you why they're hard examples. And then you will see how the methods that I talk about will approximately help us solve them. So the first one is just a classical hypothesis testing question. And what I want to test is some composite null hypothesis, which is potentially not very structured. So the setting is just the following. I give you n samples x1 through xn from some distribution p theta star. This is the classical hypothesis testing setup. I just want to test some null. Is theta star in some subset of the parameter space theta naught? Alternatively, is the distribution in some subset of the possible of my statistical model piece of theta naught? Or is it far away from that piece of theta naught, or does it belong to some other collection piece of theta 1? Right? So this is just a general composite versus composite testing problem. And if I asked you to design a test to test these hypotheses, you might think about it for a little while, and you might come up with a general purpose test to try to distinguish these. A very natural one is the so-called likelihood ratio test. So a candidate general purpose test statistic would be the LRT. So here, this will just be twice the log likelihood ratio, where the likelihood is, I'm going to look at the likelihood ratio, where the likelihood in the numerator, I'll take the likelihood of the MLE under the alternate. In the denominator, I'll take the MLE under the null. So I'll compute the MLE under the alternate, compute the MLE under the null, and compare their likelihoods. And roughly, if the alternate is much more likely, so the likelihood of the MLE under the alternate is much higher, I will reject the null. Right, so this is the classical generalized likelihood ratio test. And in order to do this test, however, you must somehow figure out what is the distribution of this statistic. Right? So in order to correctly control the type 1 error, you'll have to go ahead and now you've written down a general purpose test statistic, you'll have to figure out how to determine its distribution. And in your intro statistics class, you probably learned some form of this so-called Wilks theorem. And what it says is if you're in a nice regular parametric model, so a regular parametric model is one where the MLE has standard asymptotics, in those cases, and you add some more restrictions, the Wilks theorem will tell you that twice the log likelihood ratio has a chi-squared distribution, and it'll give you some formula to compute what the degrees of freedom is. And the main drawback of this is, A, it requires tons of assumptions. You need a very well-behaved statistical model. You need some very delicate relationship to hold between the null and the alternate. And even if all of those assumptions are true, you will only get an asymptotically valid confidence, asymptotically valid test. On the other hand, okay, if you're in an irregular statistical model or a non-parametric model, so in both cases, standard asymptotics will not hold. We don't even understand the distribution of the MLE, let alone the distribution of the LRT statistic. So if you're in one of these cases, it's much less clear how to proceed. You've come up with a nice statistic. It's an intuitive and useful one, but we don't understand anything about its distribution. So it's very unclear how to conduct a hypothesis test. So as simple motivating examples, you can come up with tons of them. You can think about something like testing in a mixture of Gaussians. So I give you samples from a distribution. And what I would like to know is, did it come from a mixture of 2 Gaussians or did it come from a mixture of 3 Gaussians? And you can think of this as some sort of nested set of parametric models. But they're very irregular and very badly behaved. The MLE has a reasonably difficult distribution. Even its rates of convergence are relatively poorly understood. And so it's very unlikely that one would be able to use this Wilks type idea to conduct a test. So this is just an example of an irregular parametric model. And you can also think of non-parametric models where I give you samples from a density, and what I would like to test is the density log concave or is it not? And here, once again, the MLE exists. It's a easy to compute, somewhat easy to compute thing, but it's not clear how one does a test of this form. Okay, is everyone okay so far? Just feel free to stop me at any point if anything is unclear. Okay. The other class of examples I will motivate first by some simple looking toy example. So let's think about the following problem. I give you samples from some distribution P sub mu. And what I would like is a confidence, so mu is the mean of the distribution P. And what I want is a confidence interval or confidence set for the parameter mu squared. Right, so let's think about the univariate case. This is very simple. Right, I give you samples from a distribution with some mean, and I want a confidence set for the square of the mean. It's just a toy problem. And what I want is an honest confidence set. That means no matter what mu is, your confidence set should ensure that the coverage, so the statement that I've written on the slide holds. That is, no matter what mu is, your confidence set must cover mu squared with probability at least 1 minus alpha. Okay, so why is this a hard problem? Well, okay, so first let's figure out how one might try to tackle the problem. We know very well how one would estimate mu squared. So this is a standard thing. You would just use a use statistic. So if I give you samples x1 through xn and you want to estimate mu squared, the canonical estimator will be just a use statistic. So in this case, it will be this thing that I've written down, which is just a second order use statistic. So a good point estimate of mu squared would be 1 over n times n minus 1 of the sum of xi times xj, where I and j are different indices. So this is just a standard use statistic estimate of mu squared. It's unbiased for mu squared, which is why it's called a use statistic. And you might think, okay, if I have a good point estimate, I should just figure out what its distribution is and invert that appropriately to get a confidence set. And now you will run into a problem. And the problem is that the distribution of this use statistic will be different when the mean is 0 versus when the mean is not 0. So when the mean is 0, theta hat will have a chi-squared distribution. And when the mean is not 0, it will have a normal distribution. And it will have these distributions with, so it will be a chi-squared scaled by n, or a normal with variance 1 over n. So they will have even different scalings. But at the very least, the distribution will be different when mu is 0 and when mu is not 0. And this makes it somehow hard to figure out how to construct a confidence set for this parameter. Okay, so you might think, okay, well, I don't need to do that. If I understand point estimation, then perhaps I can just use the bootstrap. And so this is an alternative here. You could just use some sort of resampling method. So you create your bootstrap samples, and then you create your bootstrap replicates of this estimate, and then try to do something with it. In order to check that the bootstrap is actually valid in this problem, or in any problem, you have to check some technical condition. It's called Hadamard differentiability. Checking this itself is often not trivial. In this case, it will fail. And okay, you can sort of see why it fails based on stuff I've already said. The fact that you have these different rates of convergence already implies that something like Hadamard differentiability has to fail. And the other alternative is that you can use subsampling. And subsampling doesn't require Hadamard differentiability, but in order to use subsampling to construct a confidence set, one thing that you need to know is what is the rate of convergence. That is, how fast is your estimator converging to the truth? And it'll turn out that in this case, because the rate of convergence is different at the null when mu is 0 and away from the null when mu is not 0, subsampling will also fail here. Okay, so maybe what is the summary of this whole thing? These resampling methods are often a very good idea when you understand point estimation and you want to do inference. A very reasonable thing is often to use resampling methods, but they either require you to check some technical condition, which often will fail, or if you're using something like subsampling, you at least need to know the rate of convergence. Okay, so all these methods don't really work in this problem that I've talked about. Now, this might seem like a silly toy problem, but I will try to convince you that this type of behavior actually comes up quite a lot. It comes up a lot in semi-parametric statistics, but I won't tell you why. It also comes up in non-parametric statistics, and here it's easier maybe to see what happens. So here's a non-parametric confidence set problem. So I give you samples, sort of like a 2-sample testing type problem. I give you samples from P and I give you samples from Q. And what I would like to do is estimate some notion of distance between these two distributions. One notion of distance that is very nice to use and one that can be unbiasedly estimated is the so-called maximum mean discrepancy. If you haven't heard this term before, I haven't seen this before, it doesn't matter. You just specify some sort of kernel. And what the statistic is it says how similar are samples from P, and plus how similar are samples from Q, and then subtracts off how similar samples are from between P and Q. Okay, so it's some sort of cross-match statistic. If you've seen cross-match before, you've sort of seen things that look like this. And the intuition is very simple. If P and Q are the same, you should imagine that the mean of this quantity will be 0. If P and Q are different, then hopefully it will be big. And it's some notion of distance between the two distributions. And once again, you will see that exactly the same behavior will happen. When P and Q are identical, the limiting distribution of the MMD squared will be an infinite sum of chi-squareds. And when P and Q are different, it'll have a normal limit. And so again, the same thing, the same behavior that happened with this mean squared example will happen here as well. And I will claim without explaining myself that this actually happens quite a lot. So essentially every measure of dependence, conditional dependence, or distribution distance, all of these measures of association will have some property like this, where at the null, where the two distributions are the same, or your distribution is in fact independent or in fact conditionally independent, then a statistic or a quantity that measures how far you are from independence or how far you are from conditional independence, all of these statistics will have some sort of degenerate distribution when the null is true, and will have somehow a different distribution when the null is not true. Okay, so this mean squared behavior just happens a lot in a lot of other problems. And this usually doesn't affect testing. So if you just want to test are P and Q the same, that is, you want to do a 2-sample test, then all you care about is the behavior under the null, and you don't care about the fact that the behavior under the null is different from the behavior under the alternate. However, if you care about actually constructing a confidence set for this type of measure, so you want to know how dependent are they or how far from identical are the two distributions, then you might want a confidence set for these types of parameters, and then you will have to solve this problem somehow. Okay. There will be lots of other examples of these types of parameters. I will talk about one in shape constrained inference. If you look at our papers, you will see lots of other cute examples of things like this where interesting things happen. Okay. Now, with all of that background, hopefully I've convinced you that there are some hard inference problems, even though they seem sort of benign, they are actually reasonably challenging, and existing methods maybe don't work very well for them. So now, let me first talk about how one might tackle the first set of questions where I just want to say test a composite hypothesis, and then I'll come back and talk about how we construct confidence sets for these mu squared parameters. Okay, so the thing that I'm going to talk about is this so-called universal confidence set. So here's the method. I'll describe the method. I'll show you why it's valid, and then we'll discuss a little bit more about it. So I'm going to use sample splitting, so it'll be convenient for me to think of, okay, I give you 2n samples from some distribution p theta star. And what I would like for now is just a confidence set for this parameter theta star. So what I'm going to do, so I'm going to split my data into 2 pieces. I'll call them D0 and D1. And on the second half, that is on this half D1, I will compute any point estimate that you feel like, anything. It can be the MLE. If you would like, you should think of the MLE. Compute any point estimate theta hat 1. And on the second half, I'm going to use the other half of this data to try to construct my confidence set. And what is the set? It's just going to be, I'm going to collect all the distributions that have likelihood on the first half, on D0. They have likelihood that's at least alpha times the likelihood of this point estimate theta 1 hat. Okay, so it's you should think of it as I'm just collecting all the distributions that have sufficiently high likelihood relative to this other distribution that I estimated using the other half of the sample. If you prefer, this is some level set of the likelihood ratio of the likelihood curve. So that is, I'm taking some set of distributions that have sufficiently high likelihood, and I'm collecting them all and saying this is your confidence set. Okay, so this is the universal set. And what is the claim about this set? And we'll prove it in a second. The claim is that this is an always valid, so it's a finite sample, valid, honest confidence set. That is, no matter what theta star is, the probability under theta star that theta star is in this set is at least 1 minus alpha. Okay, alternatively, the probability that you fail to cover theta star is smaller than alpha. Is everyone okay with both the construction of the set and the claim? So I just split my set. I use half of it to get some guess of what the parameter is, and then I use the other half to figure out what should be in my confidence set. All right, so let's see why this works. And the proof will be a very simple application of Markov's inequality and a cute fact about likelihood ratios. So let's see what this is. So let's just check. What's the probability that theta star is not in my set, in my universal set? This is the same as the probability that the likelihood of this theta 1 hat, which is some other parameter, over theta star is bigger than 1 over alpha. So this is, you should just trust me for now, this is the same thing. And you can just directly apply Markov's inequality and see that this is less than alpha times the expectation of the likelihood ratio. The likelihood ratio of this candidate parameter theta 1 hat to the true parameter theta star. Okay, so in some sense, I'm done if I can convince you that the expected likelihood ratio is at most 1. And this turns out to not be hard to check. And this is where sample splitting will help us. Right? So what am I going to do? I want to compute the expected value of this likelihood ratio. I'm going to condition on the second half on D1. And so theta 1 hat will just be some fixed parameter. And I'm looking at the likelihood ratio of some fixed parameter to theta star. And I'm saying, what is the expected value of this? And this, okay, you can just write it out. So you can write it out as an integral, and the expected value of a likelihood ratio will just be the expected value of p theta hat over p theta star multiplied by p theta star. So it'll just be some integral of some density, and that will be at most 1. Okay, so this expected likelihood ratio is always upper bounded by 1. And so your miscoverage probability will be upper bounded by alpha. Okay, so this was the proof of that claim. So just by splitting your sample and using this threshold, instead of trying to figure out what the distribution of the statistic is, you use a universal threshold of alpha, right? So, and once you do this, you will get a confidence set that works. So you finite sample valid, and the proof of validity is just this one page. Okay, now let's go back to the problem that I used to motivate this whole thing, which was I want to do a likelihood ratio test. So I want to do something that's roughly like a likelihood ratio test between a composite null and a composite alternate. And again, the exact same idea that I used to construct a universal confidence set, I can use to construct a universal test. So here again, what's the setting? I observe 2 ensembles from some distribution. I want to test the null hypothesis that theta star is in some subset theta naught. What do? I split my data into 2 pieces. On D1, again, I compute any point estimate. You can think for now that this is the MLE under the alternate computed using the second half of the sample. On D0, you compute the MLE over the null, and you reject the null if the likelihood of the MLE under the null over the likelihood of the MLE under the alternate, just noting that the MLE under the alternate is computed using a separate sample. If this likelihood ratio is less than alpha, you reject the null. Okay, so it kind of looks like a likelihood ratio test, except the likelihood in the denominator is computed on a MLE that was computed using a separate sample. So it's some sort of split likelihood ratio test. So this is the test. And what is the guarantee? The guarantee is, again, exactly, you can prove it in exactly the same way that I proved the previous thing. But what it says is it always controls the type 1 error uniformly over this collection of null distributions, right? So no matter what theta is in theta naught, the probability that this test will reject the null is up at most alpha, right? So it's a valid test in the sense that it controls the type 1 error correctly. Again, there's no asymptotics. There's just one simple application of Markov's inequality, and that's all there is going on here. And you should view this somehow as a very nice conceptual reduction. And what it says is that if you can compute the MLE under the null, you can construct a sensible likelihood ratio type test for that null. So this is what we have somehow achieved by all of this. Just by splitting the sample, we have reduced, you don't have to now figure out what is the distribution of the statistic and what's not. You just use this threshold of alpha. So if the likelihood ratio is less than alpha, you reject the null. And as long as you can compute the MLE under the null, this test will control the type 1 error for you. Okay, so we've somehow avoided a lot of difficult analytical computations. If you have questions, again, stop me.
Hi, Siva. Oh, it's great method. So personally, I have one question. So people generally, when people are doing the sample splitting, I think people would do it multiple times and then use combined results. So And sometimes that will restore some efficiency, especially in this cross-fitting that, there's a tons of literature in causal inference, and you can actually show that you can improve recover some efficiency there. So do you think that would something similar, like is it, I can see that it's just doing once and it works and you have all this guarantee, but would there be any reason of doing, the traditional way of sample splitting multiple times and combine them, or that will actually make things worse because we might be doing the test multiple times? So I'm just curious about that.
So yeah, so yes, you can do exactly what you said, which is you can do something like CrossFit where I swap the roles of D0 and D1, and at the end of the day, okay, instead of so I will compute all of these statistics on, say, different folds, different whatevers, as long as each of the statistics has this independence built in. And at the end of the day, I will average all of those. And the same application of Markov will tell you that it's valid. And so you can do everything that you just said. You don't lose anything. You gain something. And so we've done this calculation in just the Gaussian case. You gain something, you don't restore full efficiency. So yeah, you gain something for sure for doing it. In practice, it seems to help a little bit, but you don't expect to gain full efficiency, and you don't. Even in cases where you can actually do this computation, you don't.
I see. So at least you don't lose anything, right?
Yeah. Yeah. And the reason is somehow because you're only looking at some expected value, you don't have to Bonferroni or anything like that.
Yeah, because it still works. Yeah.
Yeah, as long as you just average your statistics, that's still valid. So the average of these split LRT statistics done in various ways will yield a statistic that will have the same property.
Okay, great. Okay, great. Thank you. Thanks.
Okay.
Oh, I have a quick question, if that's okay.
Yeah.
So I know you mentioned earlier that like one possible example is testing like how many mixtures to add in for like the mixture model. So do you have to have that the alternative hypothesis or the null hypothesis has to be true? Or like what happens if neither the alternative nor the null is true?
You have to say what you want. Like in some sense, in a testing problem, if neither the null or the alternate is true, then you just can't make an error, right? So I don't know, you can either reject the null or not, but you haven't made a mistake. So I guess you get those for free. In a confidence set construction problem, you can ask this question: do I need the model to be correct, or what happens if the model is wrong? In a testing problem, it doesn't make so much sense. In a confidence set construction problem, this is a valid concern. That is, I give you samples, I'm trying to construct a confidence set for something, but what if the entire model is wrong? Does this method somehow sensibly cover some notion of a projection parameter? And I'll revisit this question, but the answer is no to that.
Okay, thank you so much.
Okay, so one immediate concern that might come to your mind is that, okay, I use Markov's inequality somewhere. That sounds like a terrible idea. And at the very least, it would seem like the dependence on alpha should be entirely wrong. And that at least if I use something like Chebyshev or try to bound some moment generating function, use Chernoff, I should get something better. But one thing that maybe is worth noting is that somehow this Markov inequality application should really be viewed as an application of a Chernoff bound. So what do I mean by that? When we look at this fact that the expected likelihood ratio is less than 1, one should really view this fact as saying the expected value of the exponential of the log of the likelihood ratio is less than 1. And the reason for this is maybe the log of the likelihood ratio sort of behaves like a sum or an average of random variables. It is the sort of random variable that looks chi-squared under some asymptotics. And what we're using is the very non-trivial fact that the MGF of the log of the likelihood ratio is always has this valid bound. That is, the expected value of the MGF is always at most 1. So we're actually somehow, this application of Markov is implicitly using some sort of moment generating function bound. And this has some manifestation, which is when you try to do some width computation and you say, okay, fine, you constructed a valid set. What does its dependence on alpha look like? And I will try to convince you of this fact at some point, that these sets will typically have the right dependence on alpha, and it will look like square root log 1 over alpha. So it will look as though you applied some sort of Chernoff bound and not as though you applied Markov. Okay, this doesn't make sense. You can just ignore it, but really just think of this fact that the expected likelihood ratio is less than 1 as being some sort of moment generating function bound. And so it's not as silly as it sounds. Okay, to motivate this method, at least the confidence set construction method, one way of doing so is to take a testing viewpoint. And again, maybe this will help some of you think about what this method is doing. So here's the definition of the confidence set again. This is the universal set. And let me just remind you of some fact that is well known, which is that in order to construct a confidence set, one way to do this is you invert a family of tests. So suppose I have a family of tests that controls the type 1 error for testing any particular point null. I can always invert this family of tests to get a confidence set. And the idea is just, I will go around testing each of my parameters. I will collect all of the ones that are not rejected. So the ones that I fail to reject, I will collect them all together. These are things that my data is not sure whether these models, these distributions generated the data or not. I will collect all of them. And as long as your tests controls the type 1 error, this set will have the advertised coverage. Right? So this is just a general purpose way of constructing confidence sets, is you take a family of tests and invert them. And when you think about this, okay, this gives you some way to construct confidence sets in some generality. It's very underspecified. It doesn't tell you what is a good test to invert. What should I be trying to test against? Right? I'm testing is theta star equal to theta naught for each of the theta naughts in my model, but what am I testing against? And the one way of thinking about universal inference is that it's resolving this problem by some sample splitting idea. So what it says is, okay, if you want to construct a confidence set, which is small, maybe one thing that you should try to do is to test against a good point estimate. So you compute a point estimate on a separate sample and you test against that. And the idea being that, okay, if I get a good point estimate, then many things will be rejected relative to that one, and maybe my set will be small. Right? So one way of trying to design this family of tests is to say, I'm going to test against a particular fixed parameter, and that will be a parameter I compute on a separate set that is a good point estimate. Right? So to summarize, this is maybe just one way of thinking about how to design these tests. You split your sample, you construct a point estimate theta 1 hat on a separate sample, and then you try this simple versus simple test. You design a test to distinguish these two hypotheses, and now invert this. And this will essentially give you the universal set. And once I tell you it's a simple versus simple testing problem, you also know how one should test these. The natural way to test a simple hypothesis, a simple null against a simple alternative, the optimal test is just the Neyman Pearson test. And that's exactly what we're doing. We're just doing a Neyman Pearson test for distinguishing these two things and then inverting that sequence of tests. And that's the whole idea. So one way of thinking about this thing is you use sample splitting to get a theta 1 hat, and now you invert this family of tests. And the natural test to use to distinguish these is a likelihood ratio test. Okay. Let me tell you a couple of basic properties of these sets. This is just sort of standard sanity checks. If you're in some low dimensional regular parametric model, so it's one where maybe we understand the distribution of the likelihood ratio statistic, then you can see that using this sample splitting will not actually cost you anything. In some sense, if your pilot estimate, so you can prove the following general claim, if your pilot estimate is root n consistent, then, and you're in a regular nice parametric model, then the universal set will have width that scales like 1 over square root n. And as I pointed out before, you'll get this right log 1 over alpha dependence. So in some sense, its width up to constants at least will be optimal. You can try to more precisely pin down what these constants are. And so one computation that you can do is to try to do this in some sort of Gaussian model. So where you say more than just being a nice regular parametric model, the model that you're trying to do is that you have is you get samples from a Gaussian distribution and you'd like a confidence set for the mean. And you can do this in even under high dimensional asymptotics, so where D and N both scale. And one computation that we did in the paper is that, okay, you can check that the width of the universal set is within a factor of 2 of optimal. And so no matter how you pick dn and alpha, you haven't lost more than a factor of 2 by doing the sample splitting. Okay, so these are both sanity checks in the sense that these are just saying, okay, if there are other methods that I knew that worked, so if I knew somehow roughly what was optimal, this universal set is not that far from it. And the main advantage, as I maybe emphasized earlier, is that it's applicable in a lot of scenarios where we don't understand these types of methods. So it's applicable to a much broader collection of problems. I will skip this slide, which is just going to tell you how one studies the size of the set. So, and it's sort of a cute fact about likelihood ratios, which just tells you that if some distribution is far away from the truth in Hellinger, then likelihood ratios are exponentially small. You can combine this fact with the union bound to study the size of, or the width of this likelihood ratio set. For those of you who are curious, I'll just leave it up for a second. But it's just saying, okay, we sort of understand properties of likelihood ratios. And once you do this, you combine it with a union bound in the right way, then you will end up with these nice width bounds that I was talking about. Okay. So as Yenchi asked, one of the many extensions that you can try is the so-called crossfitting. You can do many other things. You can do like use many different splits and compute statistics in various ways and combine them in various ways. All of these things will have the same validity guarantee that the single split likelihood ratio test has. You can also do other things, like you can say likelihoods maybe, or likelihood ratios are very brittle to things like outliers. Maybe you can use things like powered likelihoods, so that as you raise your likelihood ratio to some power less than 1, you can check that this fact that I said that the expected likelihood ratio is always upper bounded by 1, that fact holds for powered likelihoods as well. So the same idea continues to work even if you take your likelihood ratio and raise it to some power less than 1, and this will give you a little bit of added robustness. You can do many other things. There are lots of fun extensions to think about. So if anyone has questions about some of these, I'll be happy to answer them, but otherwise, let's just keep moving. Okay, so this was the other question that I got, which is what is the main drawback of this whole thing? Well, one of them is that it's entirely likelihood based. So it means that I need a fully specified parametric model in order to even start thinking about this type of question. So for instance, in that mean squared example, I just said, I give you samples from some distribution with mean mu. I didn't say anything about what is the form of that distribution. And so it's not so clear how one would apply universal inference in that type of setting. So one thing is that you need to be able to make sense of likelihoods in order to use the method. The other, which is maybe more alarming, is that, okay, you need a correctly specified parametric model. That is, this type of coverage guarantee relies very heavily on this fact about likelihood ratios. That is, the expected value of a likelihood ratio is always upper bounded by 1. And this fact is just false when the model is misspecified. So that is, if I give you samples from some distribution outside my statistical model, what I would like is a confidence set that covers some notion of projection parameter. That is, it covers the projection of the sampling distribution to the statistical model. Such a thing will just not be true. Right? So if your model is incorrect, and I define theta star to be the KL projection parameter, this nice inequality that we had about likelihood ratios is not true anymore. And so universal inference will not have any coverage guarantees. Okay, so the two main drawbacks. One is, despite its assumption-like validity, it still needs a correctly specified parametric model, and it needs a fully specified parametric model. Okay, so with that in mind, let me tell you very quickly about the other method. And this, again, is a method to try to address this mean squared example or mean squared type examples. So first, suppose I focus on a univariate parameter. Right? So, and here's the idea. I'm going to think about theta hat as a consistent point estimate of theta star. And what I'm going to do is, instead of doing something like the bootstrap, where I bootstrap resample my data and then compute my estimate on the bootstrap resamples, I'm just going to use sample splitting. I'm going to take my data, divide it up into B buckets of size n over B. I'm going to compute my point estimate on each of these B buckets. So it's like resampling, but I'm not really resampling anything. I'm just splitting my data into a bunch of pieces. And now I'm going to try to use these B replicates of my point estimate in order to do inference. So intuitively, you might expect that with some reasonably high probability, the true parameter theta star should be in the range of all of my point estimates. That is, at least if I take some non-trivial number of splits, the minimum and maximum, which is the range of all of my estimates, hopefully will cover the parameter. Okay, so one can ask, okay, is this even true? When is it true? And what is the probability with which this is true? Okay, so this is going to be the Hulk procedure. We're going to just take our data, split it into B pieces, compute our point estimate on each of the B pieces, and then take the convex hull of all of them, which is in this case, since you're in the univariate case, it's the range of all of your estimates. Okay, so now let's just try to understand, does this work? It sounds like a horribly nonsensical idea. So let's just think about it for a minute. So let's do a basic calculation. So suppose that for a second, each of my point estimates has the property that it's symmetrically distributed around theta star. That is, the probability that it's less than theta star and the probability that it's bigger than theta star are both 1/2. Okay. If this were true, then you can sort of very quickly do this computation. So the probability that theta star is not in the range, it's like you have to toss a bunch of B coins and you will fail if you get B heads or if you get B tails. Otherwise, this interval that you have constructed will in fact cover the parameter. So you can get unlucky and all of your point estimates can land on one side of theta star, in which case you will get unlucky. And so now you can say, okay, what is the probability that you get unlucky? The probability that you get unlucky would be exactly this number that I've written, which is 2 to the B minus 1. And I want this to be less than alpha. So I'm going to take some log 2 over alpha splits. Okay, and once I take log 2 over alpha splits, I can ensure that whatever this miscoverage is at most alpha. And maybe what is initially surprising about this is that this is in some sense, if you think of alpha as 0.05, this may be something like 10 splits. And all it's saying is that you have to do 10 splits of your data and you get 0.05 coverage or 0.05 miscoverage. And importantly, this is just some constant if you are a theorist. All right. Okay, how does one generalize this idea? This is sort of assuming that the distribution of your point estimates is symmetric around theta star. If you're not, then you can sort of quantify how asymmetric it is. And the intuition, again, should just be if your point estimate is not pathologically asymmetric, then something like this method should still work. So this is the key point. If your point estimate is not pathologically asymmetric, that is, it's not always on one side of the truth. If that isn't the case, then you can sort of quantify this. You can say, what is the median bias of your point estimate? So this is just what is the distance from half of, or how skewed is its distribution? So there's some probability that it's bigger than theta star and some probability that it's less than theta star, and you subtract this from half. So this is the median bias. And this is just saying how skewed is the distribution of your point estimate. We call this thing delta. And you can now repeat the calculation that I did before. You can see that the miscoverage probability will now be bounded by something which is a function of delta. Right? So now you're tossing this coin. It has a bias. It has a bias of delta. So it's like probability of heads, say, is half plus delta, and you will fail if you get B heads or if you get B tails. You can do the same computation and it'll work out to be this number. So the probability of miscoverage will be upper bounded by this thing. And again, you can now choose B to ensure that this is at most alpha, and this will require some knowledge of delta. But supposing you know what the median bias of your estimator is, this will give you some strategy. It will say, you just split your sample into something which is roughly log 2 over alpha number of buckets. You compute your point estimate on each of them and take the range of this. And this will have some coverage as long as, yeah. Okay. All right. So you can apply this in many cases. So one is, okay, so if you don't know delta, you can try to estimate it, and we'll talk about that next. But the other case in which you can use this is if delta is asymptotically vanishing, so that is your distribution of your point estimate is asymptotically symmetric. Yanchi, you had a...
Yeah, just 10 minutes. Just
okay,
not.
I will try to wrap it up. Yeah. Yeah, so so you don't need that the median bias is exactly 0 as long as it's asymptotically 0. So, and this will often be the case if your point estimate is asymptotically normal and centered at the truth, then you will have this asymptotic symmetry property, and that's already enough. Once you have this, you will get asymptotically valid coverage using this Hulk thing. This maybe is not the most interesting case. The more interesting case is when you have some asymmetry, you can try to estimate what the asymmetry is. And you can do this, now it'll get a little complicated, but you can do this using subsampling, right? So if you don't know the median bias, you can just estimate it by subsampling. And so this is just what the subsampling estimate is. You pick your subsample sizes, kn, and you compute this quantity, it'll give you a consistent estimate of the median bias of your estimator. And once you know it, you can plug it into that formula and decide how many splits you should make. Right? And again, this will, once you show that delta hat consistently estimates the median bias, which you can often do, this will lead to a valid confidence interval. And the subtle point here is that unlike subsampling, in order to, this subsampling estimate of the median bias is very different from using subsampling to estimate the distribution of theta hat. And we have somehow given up on trying to do that. Rather than try to estimate the distribution of theta hat and use that to construct our confidence interval, we're just trying to use subsampling to estimate the median bias of your point estimator. And this turns out to be a much, much easier task. It doesn't, for instance, require you to know what the rate of convergence is. And all right, and okay, this fact I will just ignore. You still have to pick this subsample size. So this adaptive Hulk introduced another tuning parameter. It'll turn out that it's very insensitive to what the choice of this is. It's a little difficult to convince you this is a good idea very quickly. So I'm just going to do it by picture. And I will do it by trying to motivate a sort of hard problem in shape constraint inference. So here's the setup. I would like to construct a confidence band for a function. And what I know is that that function is monotonically non-decreasing. That is, it goes on. So we have some shape constraint on the function, and I'd like a confidence band for that function. Right, so this is the setup. You should imagine this sort of red line is your function. You observe some noisy version of it. So I observe it at some points. And I would like to construct a confidence band for it. Okay, so this is the goal. So let me first tell you why this is hard. So why this is hard is because the pointwise asymptotic. So okay, what is a natural estimator here? You would use the MLE, which is you would find the best fitting in the squared sense monotonically non-decreasing function. This has a name, you can compute it. And the asymptotics of the MLE are known pointwise, but they have some very weird form. So what happens is the following. If you're in a region where your function is increasing, then you get some non-standard rate of convergence. The MLE will converge to F star at some n to the 1/3 rate. And the limiting distribution of the MLE will be this so-called Chernoff distribution. It's analytically not tractable distribution, but yeah, we have some understanding of what it is. What is even more interesting is that if the function is not strictly increasing, that is, it's somehow flat at the point x0, so we're talking about some pointwise asymptotics, then the MLE will have a faster rate of convergence, and it will converge to a different distribution. So like our mean squared example, you get different behavior where the function increases, you get different behavior where the function is flat, and it'll have a different rate of convergence to a modified Chernoff distribution. Okay, so this means that it's going to be very difficult to use these type of pointwise asymptotics to construct a confidence band. But of course, you can just use the Hulk. Both of these distributions turn out to have median bias of 0. So you can just apply the Hulk, by which I mean you would take some grid of points, compute your your MLE on B different buckets of the data, and then take the range at all of these points, and then interpolate them to get the confidence band. Since you know your function is strictly increasing, you can do some Bonferroni thing, and you'll end up with this picture that I'm showing you. And what is nice about this picture is that you will see this nice adaptivity property. So the MLE has this very nice adaptation, which is when it's increasing, you get n to the 1/3 rate. When it's flat, you get a much faster rate of convergence. And what you would like is that your confidence bands inherit this adaptivity. Ideally, you would like confidence bands that are very narrow where the function is flat and sort of wider where the function is increasing, because this is roughly how the MLE itself behaves, and you would like your inference to reflect this. And you will see that these Hulk bands actually do reflect this property. Okay, so maybe the big takeaway from here is that you just apply this method. You don't need to understand anything about the limiting distribution, and you still get this nice adaptation, which is you get narrow confidence bands in some places and wide ones in some places. 5 more minutes? Okay, cool.
Yes.
Okay, I will skip this just so I can get to the punchline of the whole talk, which is, okay, you can do some width calculations. The nice thing, as I said before, at least if you're a theoretician, what you've lost is some square root log factor by splitting your sample. And okay, this is maybe not as much as you might have expected. And it gives you inference in a lot of nice examples. So if you go back to this mean squared example, this U statistic that I described, it's almost a symmetric distribution. It has some slight bias, but it's not very big. And so you can use the Hulk to get inference in that case. So you just, in your mean squared example, you would apply your U statistic a bunch of times and take the range of the estimates that you get. And I claim that you can very easily see that this will be a valid interval. Right. So this maybe goes into some more detail of some width computations for the Hulk. You can do a multivariate extension. I talked about a bunch of things in univariate cases. It's not very hard to extend. I will skip that. And maybe I will just get to the punchline about the Hulk. You should compare the Hulk to something like a walled interval. And one of the key things will be that you don't need to estimate the variance of the limiting distribution. So if you want to apply a walled interval, you need to estimate somehow the parameters of the limiting distribution, and the Hulk somehow doesn't need to do this. For instance, this can be an annoying thing to do. For instance, if I wanted a confidence interval for the median, I know something about the limiting distribution, but if I want to use a walled interval, I will need to estimate the density at the median, and this can be quite difficult to do. You can compare the Hulk. Okay, so maybe Hulk versus walled. Hulk removes the necessity to compute variances. Hulk versus bootstrap, because you've sample split many times and you're not reusing the same samples and you're not trying to approximate the entire limiting distribution, you get a lot of benefits. That is, it is valid under much weaker conditions. It's valid as long as you have a non-pathologically asymmetric point estimator to begin with. And this maybe at some level avoids having to check conditions like Hadamard differentiability. It works in all of these mean squared type examples. So where you have different behavior at the null and different behavior away, as long as your estimator is, say, unbiased, which it is for the MMD or for the U statistic, you can just apply the Hulk. Okay, so now let me just very, very quickly just summarize the whole talk. So I introduced 2 assumption-light methods for inference in irregular problems. You should think of the first one as some sort of split likelihood ratio method, where it makes likelihood ratio inference much easier, where you get all these universal thresholds. You don't have to reason about limiting distributions. And the other one is the Hulk, which you should maybe ideally think of as some sort of comparator to subsampling or the bootstrap. It's some variant of those types of methods. But because it uses full sample splitting, it gives up some efficiency, but it makes it valid in a lot of cases when those other methods are not. These are extremely broadly applicable. One thing that maybe I didn't spend enough time on is that you can do these width computations, and maybe you would be surprised at how little you lose, at least in theory. Okay, some broader context. You should really think of irregular problems being everywhere in statistics. I gave you a few examples, but they arise quite a lot. There are lots of problems where we don't understand limiting distributions of our estimators, but we'd like to still do inference. And these types of assumption-like methods present some sort of interesting trade-off. They're very easy to use. You don't have difficult regularity conditions to check. There's no complex calculations. And in some sense, it fits in this broader body of literature of things like conformal inference and so on, where you get validity, you focus primarily on validity, you get it under very weak assumptions, and then you lose a little bit in all of these other dimensions of this problem. Okay, I will stop here.
Okay, thank you, Siva. It's really great and insightful talks. And any questions from the audience?
I have a quick.
Oh, you go ahead, Alan. Your question was great.
I'm just curious if there's any comparison between, I know you mentioned confidence intervals in the previous project with the universal likelihoods. Is there any comparison with the Hulk method versus the confidence intervals you would get from there?
Yeah, I usually think of them as being, you should apply them to two different sets of problems, in the sense that, and they're sort of, the two examples I gave are the canonical ones. I would use universal inference if I had a correctly fully specified parametric model. So if I can write down likelihoods and they make sense, then I would use universal inference. And in these examples like mean squared, I can't do that. And then I would suggest something like the Hulk. In terms of directly comparing them, if both are applicable, almost certainly universal will be better because it does a single split versus the Hulk, which does many splits and will lose proportionately much efficiency. I don't know if that makes sense.
Okay, so next is Amy, and then Steve and David.
Thanks so much, Siva. That was a fantastic talk, and any work towards making reducing the need for analytical calculations is something I'm absolutely going to love. My first question, and then I'll let other folks ask their questions, was that you had this nice argument about widths being more Chernoff-y than Markov-y. And so I was wondering, do you have any examples where your split likelihood ratio test confidence intervals are the best you can do? Maybe coming from a situation where your Markov bound is exact. I don't know if you have if we have test statistics like that.
I don't, but I would guess this would never be the case. Once you've done sample splitting, you have at least given up that factor of 2 or something somewhere, or you can try to recover it using things like crossfitting, but you almost certainly will not recover it fully. And so I would guess there are no, this sounds silly, but there are no problems where it is exactly the most efficient method to use.
Okay, yeah, and I guess you're right that it's a stochastic method anyway, so you need to be talking about it being like with high probability, having exact coverage. Cool, thanks so much.
Okay, great. Next one is Steve.
Hi, thank you for the great talk, first of all. So one of the things I was kind of thinking in this likelihood ratio context is, so obviously the sacrifice here is like, you might sacrifice power for getting this finite sample validity. One particular example I'm thinking of is like if you had sort of a high dimensional discrete variable, and you mentioned that sort of you can use any estimator on your D1 data set. And you kind of mentioned like the maximum likelihood would be one way to do this. But in kind of this setting, you might have a lot of cases where one pattern that occurs in D0 or one category that occurs in D0 doesn't occur in D1, and then you're instantly getting a value of 0 for your test statistic, which seems like maybe this is not the best idea, but can you give any sort of guidance on other estimators of theta1 that might help give a better power, or is this a kind of situation you see happening in other test settings?
Yeah, so I would do some weird pseudo count thing in that kind of example. So if you have like a high dimensional discrete thing, yeah, there's any likelihood ratio based thing will be very brittle to seeing zeros. And if you split sample, you will see many more zeros. So it's, I don't have a good answer. I would regularize your, whatever your categorical multinomial estimate in some way by maybe hallucinating some set of counts or hallucinating some fraction of counts in all of the bins. This might be a terrible idea in practice, especially, yeah, I can imagine lots of cases where it's a bad idea. So I don't have an answer to this. You probably should not be using likelihood-based methods at all, but that's very unsatisfactory of an answer, but I don't have a better one.
Thank you.
Okay, thanks. Next one is David.
You're muted.
Yeah, David, I think. Yeah.
Sorry about that. Thanks for a great talk. I had a question about the isotonic regression example for the Hulk. I'm assuming, maybe I'm wrong, that you're getting pointwise intervals. Is that right?
I'm born for owning and getting pointwise intervals. Yes.
Okay. I'm curious. Like, can you apply this if you? So it seems like the reasoning is like this reasoning about median bias works really well if you have a parameter, or if you're able to, reason about your parameter on the real line. if I wanted coverage for the whole curve, is this something I could apply, or would I run into trouble?
So for instance, I don't even know how one does this for non-parametric regression. So shape constraint is nice because I can do it on a finite grid and interpolate to get a band.
Right.
I don't even know how one does this on, so for a non-parametric regression, you actually have to reason about the whole function simultaneously, and that's not that trivial. And so, yeah, I don't know whether I answered your question, but I guess I don't have an answer to what one would do if one wanted to reason about something that's not like a finite object. So if you wanted a confidence band in non-parametric regression, I'm not sure how you would apply this.
Okay, fair enough. Thank you. Yeah.
Great. Amy?
Thanks so much, Yanji, and thanks again, Siva. Maybe I had a related question to Stephen and David's question, which is, do you think there's any hope of having methods like this for non-Euclidean parameter spaces? Maybe you've already talked about this with Yanji.
I haven't, but so are you thinking about universal, or are you thinking about Hulk?
Either.
Universal, I think, makes sense as long as you know what likelihoods mean on your non-Euclidean space. There's nothing particularly Euclidean about it, as long as likelihoods make sense and they are small, far away from the truth.
Mm-hmm.
You'll get a sensible confidence set. But I guess you're thinking about objects like trees, and maybe likelihoods don't make that much sense. I don't know if you have like these, maybe you do have fully specified parametric models that let you take in some tree and spit out a likelihood.
Yeah, for sure. Mm-hmm.
Okay.
Yeah,
So,
I guess David's example with or your example of non-parametric regression was another good one.
yeah. So non-parametric regression, I usually think of the standard setup. You don't necessarily, you just say you observe a function with some noise and you don't necessarily have a full likelihood. You don't know the X generating distribution and so on. So you can't really apply universal directly there. It's more promising to try to apply Hulk, but I would only know how to do this at a single point. I won't know how to do like band construction there.
Cool, awesome.
And
Thanks.
even there, you have to be very careful. This median bias condition seems sort of innocuous, but you need to, in non-parametric regression, the standard problem is you balanced bias and variance, and then it's not the case. You could be entirely on one side of the truth because of the way that you balanced bias and variance. And so
I guess I'm even thinking about how do you even define this asymmetry in your likelihoods when you have a non-Euclidean object? That doesn't even seem trivial to me. I'd have to look back at your definition.
yeah, so I mean, so let me be a bit more clear. So I'm thinking of the case where the parameter theta star is just the function value at some point x naught. And so this median bias is just saying, you construct your kernel estimate, what's the probability that it's bigger than the truth, and what's the probability that it's smaller than the truth. Ideally, if you haven't picked your tuning parameter very, very badly, you would hope that there's some chance you're above and some chance that you're below. But if you pick it badly, then you're in some trouble with this type of definition. I don't know if that answered.
Yeah, that's great. Thanks. I did have one more question.
Sorry, I didn't answer anything about non-Euclidean parameters in the sense that I reduced it to a univariate parameter and then said something about it. So I don't actually have an answer to your actually.
That's sometimes the best answers to questions. My last question, and thanks for bearing with me, was that as you've noted again and again, the split likelihood ratio test hinges so much on these likelihoods properties, and thanks for talking us through the proof that made that really clear. Do you think there's like any hope of generalizing this sort of logic to, estimates, estimators defined by estimating equations, or is that just beyond the realm of that approach?
So you're thinking of something like a method of moments type?
Yeah, for example, yeah. Yeah, M estimators generally.
Yeah, this is one of those things where I think it would be better to think about the Hulk than it would be to try to get universal to work, but just a guess again.
Okay, cool. Thanks so much. Great talk.
Thank you.
Okay, great. Yeah, I think because of the time, so any final questions for Siva? Okay, so if no other question, let's thank Siva again for this really exciting and insightful talk. Really great work, great work.
Thank you.
Thanks, and hopefully we'll meet each other soon in person.
Yeah, when my baby goes to college, I don't know if I'm allowed to say things like this on camera, but someday I will travel again. But thank you again for the invitation. It was really nice.
Very insightful work, really great. Yeah. Okay. See you. Bye.